Hey, welcome back. This is the review for test 3 for Calc 3, and I just want to kind of go through some of the example problems that will be similar to what I'll pick on the test and give you sort of a question pool on top of that. So we began with 13.1, which was just looking at multivariable functions, and all I really want to do, I'm not going to beat you up over the domain and range type issues. I just want to make sure you can evaluate these functions, in particular 3 and 4, because these are in line with the development of the partial derivatives, which we see later. So expect me to take something similar to these functions, and then you have to kind of set up the difference quotients, which eventually we would take the limit, and then you would have the partial derivative. So I'll just look at part B for this one, number 3. They give us the function, and then we want to evaluate f of x comma y plus change in y. So this would be the difference quotient for the partial derivative with respect to y. Y plus change in y minus f of x y all over change in y. Okay, so you're substituting in x and y plus change in y into the original function for this initial part. Okay, so I'll have 4x plus, instead of y, put y plus change in y squared, and then minus f of x. You have to subtract the whole thing, so put parentheses around it, please. That would be all over change in y. And then it's basically just simplify. And you should get something such that when you take the limit as change in y goes to 0 equals the partial derivative with respect to y. So in this case, it would just be 2y, should be kind of sort of your answer, right? So anyways, 4x plus y squared plus foiling 2y change in y plus change in y, the whole thing squared, minus 4x minus y squared all over change in y. The y squares cancel, the 4x's cancel. I'm getting 2y change in y plus change in y squared all over change in y. Factor out the change in y. Get 2y plus change in y all over change in y. And then we could do some canceling with the change in y's. And you get 2y plus change in y. So note, as if we took the limit as change in y get to 0, you just get the partial derivative with respect to y up here. But on the test, this would be the answer that I just put in the box. Okay, so you should be able to handle that for pretty much any function I dream up. Let's move on to 13.2. Okay. So 13.2, we started working with limits of multivariable function. In particular, just evaluating them was pretty easy so long as there wasn't some issue of division by 0. Later, when we encountered division by 0, you kind of had to do multiple approaches and show that maybe one of the approaches went to infinity, or 2 of the approaches went to different places, and that would prove that the limit did not exist. So 13.2, problems like 1 to 16, I'll sort of avoid those issues with continuity, and I think, yeah, like these later ones where we had issues of continuity of piecewise functions, I'll sort of avoid those, but anything else is kind of fair game. Anyways, let's look at number 6 and see what we have. We have the limit as xy goes to 0, 0 of x plus y all over x to the 10th plus y. Here, if you plug in 0, 0, you get 0 over 0. So it's kind of an indeterminate form. So we're going to analyze it along different approaches. So along the approach x equals y, let's try that. So we have the limit of, let's do x comma x goes to 0, 0. So I just replace y with x wherever I see it. 0, 0. I think in the videos I might have just kind of dropped this down into one dimension with just an x going to 0. But I think technically you're supposed to write it this way. Okay, so anyways, I won't take out points if you do what I did in the video. I understand what you mean. Anyways, so I have x plus x in the numerator, and then x to the 10th plus x in the denominator. You want to clean that up. So I have 2x in the numerator. I can factor out an x from the denominator of x to the 9th plus 1. One of the x's would cancel, so I'd have 2 all over x to the 9th plus 1. And we're basically taking the limit as x goes to 0. And if you plug 0 in there, you just get 2 over 1, which is 2. Okay. We're hoping to get another limit that does not go to the same place. So let's try along x equals, I think I picked 0 in my notes. So I have the limit as x comma, so wherever I see x, I'm going to replace it with a 0, so I need to put a 0 there. Okay. So 0 comma y, going to 0, 0, and then in the function, wherever I see x, I'm putting 0, so I'll have y over y. And so I'll have the limit of 1, basically, and the limit of a constant is always just the constant, regardless of where y is going. So that just equal 1. You see these two limits don't go to the same place. So at the end of the day, that implies the limit does not exist. Okay? So that was one way to kind of disprove a limit. The other way was if you could find a limit that goes to infinity in any of the potential directions. So for example, number 8, we have the limit of x comma y going to 0, 0 of the ln of x squared plus y squared. Okay. Trying the approach x equals y, we would have the limit of xx going to 0, 0 of the natural log of x squared plus x squared would be 2x squared. Okay. And if you think about the natural log, as x goes to 0, as the x values go to 0, the y values are going to go down to negative infinity. Okay, so this thing would equal negative infinity. If you can find any approach that goes to infinity or negative infinity, we just say that the limit does not exist for now. So in this case, the overall limit does not exist. Okay, but you need to show me those approaches on the test for you to get full credit. You can't just write the limit does not exist. I'm going to want to see some proof. Anyways, sometimes you could do a polar conversion, so use polar coordinates to find these things. I just want to remind you of doing that. So number 14, we had the limit as xy goes to 0, 0 of x squared minus y squared all over the square root of x squared plus y squared. So the trick is to replace the xy to 0, 0 with r going to 0. And then x you replace with r cosine theta, so you get r squared cosine squared theta. And then y you replace with r sine theta, so I have r squared sine squared theta. This will be all over basically the same stuff but added together. And then we could simplify using Pythagorean identities. In the numerator, I can factor out an r squared. Sadly, you cannot simplify cosine squared minus sine squared in a beneficial way. So we're just going to leave that alone. But downstairs, you can factor out the r squared. Then you have cosine squared theta plus sine squared theta, which of course is just 1. Okay. So it's just 1. So you get the limit as r goes to 0. Taking the square root of r, you'll just have r. So it'd be r squared over r, which is just r at the end of the day, times cosine squared theta minus sine squared theta. Regardless of what theta is, if you let r go to 0, that entire thing will be equal to 0. 0 times something is just 0. So at the end of the day, that particular limit is 0. Okay, once we figure out how to work with limits, then we move into the partial derivatives, which would just be the limit of those difference quotients that I saw in 13.1, that I showed you in 13.1. So you should be able to do any partial derivative, and then also the mixed partial derivatives if you're called upon to do so. Right, whoops. So I clicked out of what I wanted. It's going to take a little time to get back in. I need to go to 13.3. Okay, so let's look at number 11. I kind of have them already written out. So they give you this function, the square root of x plus y. We want to find the two partial f with respect to x, f with respect to y. So with respect to x, first you got a power rule, 1/2 times x plus y to the 1/2 minus 1 is negative 1/2 times the derivative of this stuff with respect to x. so that would just be 1. In other words, we get 1 all over 2 square root of x plus y. Derivative with respect to y then is pretty much the same thing, right? It's just the derivative of x plus y with respect to y, well, it's the same thing. So again, it's a power rule times x plus y to -1/2. Then the derivative of x plus y with respect to y is just 1 again. It's with the same answer. Kind of weird. Anyways, you should also be able to pull off all of the mixed partials, like in number 15 there. So we have z equals x to the 4th minus 8xy plus 2y cubed. And then let's get zx first. Okay, so this isn't really part of the answer. We want zxx, zyy, or sorry, zxx, zxy. And then over here, I'm going to get zy, y, zyx. And yx and xy should be equal to each other, especially for this case, because that thing is just a polynomial. Okay, so there's really, 6 partial derivatives for this kind of problem. All right, so anyways, partial with respect to x, 4x cubed minus 8y. Then the second partial with respect to x would be 12x squared. The partial of the derivative with respect to x with respect to y would be -8. And then on the right, the partial with respect to y would be -8x plus 6y squared. Z with respect to y is going to be so the -8x is 0, and then it's just 12. Take that in there, 12 y. And then the zyx is going to be -8 again, which it should be. Those should be the same. Okay. The next part we looked at is kind of, because we don't really have an overall derivative like we did in Calc 1. So what we did was develop the total differential. And so you should be able to kind of get total differentials given a function. So this is then 13.4. And we also use these to do approximations, if you remember. So anyways, finding the total differential is a good thing. So let's try number 2. This is 13.4, questions like 1 to 8. Let's switch to number 2. Z equals e to the -x tan y. So if you've forgotten, the total differential dz is going to be the partial of your function with respect to x times dx plus the partial of your function with respect to y times dy. So you got these 2 changes in 2 different directions, which add up to the overall change in the z direction. Okay. So writing it out then, dz, the partial of z with respect to x would be -e to the -x tan y, and then you just tack on a dx. And then the partial with respect to y would be plus e to the -x secant squared y, and then tack on your dy. Okay. You should be able to do the approximation problems, like number 8. You want to approximate 2.04 squared times 9.9.02 minus 2 squared times 9. So you use a total differential to get your approximation, but what is the function that we're dealing with, our z function, or f of x, y function? From this form, it's going to be x squared y. Our x and y values look like 2 and 9. And then our change in x and change in y look like they're going to be 0.04 and 0.02. So the approximation of that thing would be, the partial of f with respect to x of 2xy times change in x. If you want to put dx, that's the same thing. And then the partial of f with respect to y, so plus x squared delta y. And then you just substitute in the numbers right? So you get 2 times 2 times 9 times 0.04 plus 2 squared, which of course is 4 times 0.02. And if you put that in your calculator, you get about 1.52, which approximates this thing here. Okay. Moving on then to 13.5, we have the chain rule. Let's look at 13.5. So the chain rule comes up sometimes in proofs when you're trying to kind of connect the dots. You see it every once in a while there. So it's kind of important for your reading. Let's look at number 4, I guess I picked. Okay, so I expect you to do it kind of the calc way using the chain rule. I don't expect you to convert to a function of t. So you got to do it the calc way. You can't do the calc 1 way, all right? So I expected to see you to use the chain rule on the test. So number 4, w equals cosine of x minus y. X is defined as t squared, y is just 65. And I'm after the derivative of w with respect to t. So from the chain rule, that's going to be the derivative of w with respect to x times the derivative of x with respect to t. It's actually, this is the partial of w with respect to x times the derivative of x with respect to t. Plus then the partial of w with respect to y times the derivative of y with respect to t. So you just fill in the blanks then. W with respect to x is going to be negative sine of x minus y times 1, and then the derivative of x with respect to t is 2t, and then plus the derivative of w with respect to y, this time would be negative sine of x minus y times negative 1, and the derivative of y with respect to t is just a big 0. Okay. So I get negative 2t sine, and then back sub t squared and for x, and 65 and for y. And that would be your answer. Okay, you should be able to work with the partial derivatives as well when your functions x and y are given in terms of 2 more variables. So problems like number 9, w is sine of 2x plus 3y, x is s plus t, y is s minus t. I won't force you to evaluate these. Partial of w with respect to s is going to be the partial of w with respect to x times the partial of x with respect to s. Okay, so the partial of w with respect to s is cosine of 2x plus 3y times 2, and then times the derivative of x with respect to s, which is 1, and then that would be plus the derivative of w with respect to y, which is cosine of 2x plus 3y times 3 times the derivative of y with respect to s, which is 1. So I'd end up with, it looks like 5 cosine, what is 2x plus 3y? So 2, in terms of s and t, I mean 2x plus 3 times y is going to be 2s plus 2t plus 3s minus 3t, which is 5s minus t. Okay, cosine of 5s minus t. Partial derivative of w with respect to t then is kind of the same thing, right? It's just now you're taking the derivative of x and y with respect to t. So the first term will be cosine of 2x plus 3y times 2. And then the derivative of x with respect to t is just 1 again. And then plus cosine of 2x plus 3y times 3. And the derivative of y with respect to t this time is negative 1. So it's a little different. But ultimately, you add these together. There's 2 of the first one, negative 3 of the second one. You get negative 1 cosine of, again, that would become 5s minus t. Okay. Alrighty then. So chain rule, you should know how to do that stuff. 13.6, then we introduce the gradient along with the directional derivatives. I'm looking at problems like 1 to 17. So remember, when you're doing directional derivatives, you always want that unit vector. I think that's the biggest freshman mistake people make. Let's look at number 10-ish. So here's my software gets loaded, number 10-ish. So use the gradient to find the directional derivative at p in the direction of pq. Okay, so f of xy, 3x squared minus y squared plus 4, p 5, 1, q is 6, 6. So when they say pq, they mean you start at p and you end at q. So the vector pq is going to be 6 minus 5, which is 1, and then 6 minus 1, which is 5. For duff, the directional derivative in the direction of PQ, we're going to need a unit vector, right? So the magnitude of PQ, of course, is just going to be the square root of 1 plus 25, which is 26. And so our direction should be 1 over root 26, comma 5 over root 26. So you need to make that a unit vector because that's the way all of our formulas were derived. Then you could get the gradient of f. So it would just be 6x negative 2y, and then you evaluate duff at the point P, which is what it says in the directions. So duff at 5, 1 is going to be the dot product of the gradient and this unit vector. And so that's going to be 6x times 1 over root 26, and you're plugging in 5, 1 into for x and y. So 5 times 6 is 30, times 1 over root 26 is 30 over root 26. And then 2 times 1 is negative 2, times 5 over root 26 is negative 10 over root 26. And our directional derivative will be positive 20 over root 26. Okay, one thing about the directional derivatives that we learned is that the direction of maximum increase on a surface is the direction of the gradient. So, for instance, problems like number 15, where they want to know the direction of maximum increase. You're a mountain climber and you want to go straight up the mountain as quickly as possible, I guess, something like that. All you have to do is find the gradient and evaluate it at the given point. So their hill function is given as 8,000 minus 0.001 x squared minus 0.004 y squared. You're located at the point 900, 700, 5230. You want to know which direction to climb in order to have maximum increase. I guess you're really challenging yourself, so you go for the gradient, right? So the gradient of h is going to be negative 0.002x, and then negative 0.008y. And then you just evaluate this thing at the point that you're standing on. So 900, 700. So that's going to be negative 1.8 when you plug it in. And then plugging in 700 for y, you get negative 5.6. And that would be your answer. Okay, great. Good stuff. From there, we start looking at maximization and minimization problems. First, by using the second partials test. So we introduced the second partials test. And again, you will have a formula sheet that you can use. In particular, the formula sheet is just the second partials test. So if you click on that, yeah, so you're going to get the second partials test. I'm not going to force you to memorize that. Anyways, 13.8, I'm thinking of questions like 4 to 11. In particular, I'm going to look at here in my notes number 7, h of xy equals x squared minus 3xy minus y squared. Okay, I want to find if there's any max, mins, or saddle points. So you need critical numbers, but you also need all of these partial derivatives. So let me get all the partials first. So hx is 2x minus 3y, hy is negative 3x minus 2y, hxx is 2, hyy is negative 2, hxy negative 3. Okay. So first I need to get my critical numbers, and you get those from setting the first partials equal to 0. So 2x minus 3y is 0. So 2x equals 3y, so basically x is some multiple of y. plug this into the other equation. So the other equation is negative 3x minus 2y equals 0. So plugging this into there, I get negative 3x minus, I guess I went the wrong way with that, didn't I? So it'd be negative 9 halves minus 9 halves y minus 2y is 0. So, you know, negative 13 halves y is 0. Y is 0 ultimately, regardless of what I did. So that means x is also 0. And you plug y equals 0 into here. Right, so I have some kind of point at 0, 0. I need to figure out the d value, so I can just look over here to the right. The d value in this case is fxx times fyy, so in our case that would be 2 times negative 2, and then minus hxy squared, so minus 9. So that's going to be negative 4 minus 9, which is negative 13, which is less than 0, which means I have a saddle point at that point. So saddle point at 0, 0, and then plug that into the original function. Well, that's just going to be 0, so 0, 0, 0. Okay. Sometimes, you know, your hxy and hxx will be variable. So your d will also be variable, so you may have several d's that you have to analyze, and you may have different, you know, a max here, a min here, a saddle here, etc. I'm not going to put any of the boundary problems on the test; it'll just take too long. And anyways, so 13.9 is then doing optimization in the land of story problems. So basically, you'll have an optimization formula and a constraint formula, and using those two, you determine your maxes and mins. And typically, you don't have to actually do the second partials test. Usually, your answer is what it is. So let's try number 5. We want to find 3 numbers such that their sum is 8. So x plus y plus z equals 8. This is the constraint formula. And their maximum, or we want to maximize this product xy squared times z. So this is the formula we want to optimize. Okay. So the way it works is use a constraint formula to reduce the number of variables in the optimization formula. So you get z is 8 minus x minus y. And then your optimization formula will be xy squared times 8 minus x minus y. Okay, let's rewrite that as 8xy squared minus x squared y squared minus xy cubed. At this point, you need the partials, and you set them equal to 0, and the critical number usually is your answer, right? So I get px, that's going to be 8y squared minus 2xy squared minus y cubed. Py then is going to be 16xy minus 2x squared y minus 3xy squared. Set these guys equal to 0. And usually you get some sort of nonlinear system of equations. This one looks like it's impossible, but you can factor out the y squared, because we assume usually in these questions that x, y, and z are positive, right? So you can see in the question 3 positive integers. That means they're not equal to 0. So if you did factor out something like y squared, like I'm going to do, y squared can't be 0, so you can kind of just throw that part of it out. You can divide both sides by it. And you get 8 minus 2x minus y. So basically 8 minus 2x minus y is 0, and then you can solve for y. Y equals 8 minus 2x. Go to the other equation, you kind of play the same game. You can factor stuff out, xy, 16 minus 2x minus 3y. Set that equal to 0. The xy can't be 0, so you can divide both sides and get rid of it. Plug in, you know, your 8 minus 2x. So I get 16 minus 2x minus 24 plus 6x is 0. Get 4x minus 8 is 0, so it looks like x is 2. And then back sub it for y, so y is 8 minus 4, which is 4. And then back sub again to get z into here. So z is 8 minus 2 minus 4, which is, of course, just 2. So 2, 4, 2 would be the point that maximizes that thing. 2, 4, 2. All right. From there, we learned another method for doing optimization. The book advocates this method for border problems, because those border problems were, at least that's what it seemed like to me they were advocating, but then they didn't actually do any of these sort of restraint problems. So they were like, many optimization problems have restrictions on values that can be, such constraints tend to complicate optimization problems because the optimal solution can occur at a boundary point, right? So it was like the last two problems in 13.8. That's kind of what I had in my mind when they were talking there. But I don't think they actually go and do any of those kind of problems. I could be totally mistaken, but it seems like they're being a little bit misleading. Anyways, I will do some of these Lagrange problems. So that would be the last time a problem. Let's get 13.10. I didn't put a lot in the homework. I only put like 5 questions in there. Anyways, here we have a constraint formula, which is thought of as our g of x formula. And then our optimization formula, which you think of as your f of x formula. And this time we want to minimize it. Minimize. Okay. So you need the gradient. So the gradient of f is basically, I'm calling f my p thing here. So that would be 1, 1, 1. And then the gradient of g is the constraint formula. So it'd be yz. So yz, xz, and then xy. Right? So your system of equations is you set the gradients equal to each other with lambda involved. So 1 equals lambda yz, 1 equals lambda xz, and 1 equals lambda xy. And then you also have the constraint formula, xyz equals 8. So what you can do is kind of solve these things for like x and y. So I can say xy equals 1 over lambda. So I would get so this would be 1 over lambda times z equals 8. I guess let's solve for z here maybe. So z equals, well, that's not going to help very much. So z equals 8 lambda. And if I get x, y, and z in terms of lambdas, see if I can pull that off. If I take this second formula, again, I can pull that in. Xz is 1 over lambda. And then if you plug this into the xyz thing equals 8, what do you get? You get 1 over lambda times y equals 8. Whoops, my lambda, when it's upside down, looks like a y. 1 over lambda times y equals 8, so y equals 8 lambda. And then use this one to get another equation, so yz equals 1 over lambda. So using the xyz formula now, you have x times 1 over lambda equals 8. So x is equal to 8 lambda as well. Then you can plug all of this chunk into the constraint equation. And you get 8 lambda times 8 lambda times 8 lambda equals 8. So you get lambda cubed equals 1 all over, well, it's 8 over 8 cubed, which is 1 over 8 squared, which is 1 over 64. The cube root of 1 over 64 is just 1 over 4. And then you could back sub to get x, y, and z. So there's no real, in my opinion, kind of program. I just kind of fiddle around with the system until I get my answers. Z is 8 times 1/4, which is 2. Y is 8 times, oh, they're all the same, which is 2, so X then is also 2. So 2, 2, 2 is kind of our optimal solution, and that would do it, okay? Okay, so that'll do it for me. Okay, make sure you study, and thank you for watching as usual. We'll see you next time.